hello everyone. It's nice to see a rather full room for the end of the day for this very interesting talk by Julien Bedel about web-based password managers. He's going to talk about a lot of attack techniques. He will be using an example, Bitwarden for this, but this applies to much more than just Bitwarden, right? Without further ado, I'm not going to waste your time. Please enjoy Julien Bedel.
Thank you. Hello. So I hope you're enjoying today's conferences, talks, workshops as much as I did. And so for this last talk, I'm really happy to be there, talking about web-based password managers with a focus on Bitwarden. And for those interested in the slide deck, you can get it from this tiny URL link, or from this QR code if you're far away from the screen and you just want to keep it. So I'm just going to let you a few seconds to get this. It's BruCON BW like Bitwarden for the URL. All good? So I'm going to do the traditional who am I, because it's my first time here in BruCON, but I'm going to make it quick because I've already been introduced. So yeah, I'm as you can hear from my accent, I'm French. Nobody's perfect. But really happy to share this talk with my Belgian and Dutch neighbors here. And so I work as a penetration tester, red teamer, so more on the offensive side, and at this company, Orange Cyber Defense, a cybersecurity company in France. And I worked a lot on KeePass password manager because in my engagements, it's quite often that you have to, the last barrier that you need to get access to the crown jewels, let's say, it's in the password managers of the administrators. So that's why I worked on KeePass with tools like KeepOwn or KeyForce Reborn. For those of you who do penetration testing, you may have used them already. And eventually, what I noticed is that during my engagements, my clients were going more and more into web-based password managers. So KeePass was not enough, and I had to do my research to be able to extract these passwords again. And so why web-based password managers? I guess it's for the convenience, because it has cloud access, it's easy to synchronize, because obviously it's on the cloud, or it can be also self-hosted in your network. It's cross-platform, so you can have it from your mobile, from your Linux device, from your Windows corporate device, quite useful. And also you have these browser extensions, which lets you, for example, use the password autofill feature, which is quite appreciated. And because it's getting more and more used, it's also getting more and more targeted by attackers, by threat actors. So here are a few examples. On the left, it's from infostealers.com. It's a seller who is selling global, basically access to Bitwarden vaults. And on the right side, we have an InfoStealer example with these extensions UUIDs, which are hard-coded strings found in the InfoStealer. Some of them are for cryptocurrency wallets, but others are for web-based password managers extension. We can see Bitwarden, we can see LastPass. So because it's getting targeted, we are going to try and understand really how attackers operate to attack these managers and try to develop attacks and defense strategies, and if possible before the bad guys do, so that we can try to proactively protect against these strategies and so on. And in order to study password managers' attacks, we have to start somewhere. So we are going to take Bitwarden as a case study because in order to find techniques that let attackers extract passwords. And just to clarify, what we're going to do here is not looking for vulnerabilities that really are affecting Bitwarden per se, but really try to find broader techniques, generic attack techniques, which would, in theory, apply to any password manager. So let's dive in Bitwarden now. So why Bitwarden? for the case study simply because it's one of the most popular password managers. It's estimated to be around 25% market share, but we never know for sure, but it should be around the same as LastPass or KeePass, I guess. And why so popular? Because I guess it's compliant to multiple requirements, for example, here in Europe, and it's also open source, which always brings trust in a software, in my opinion. And so what does Bitwarden look like? It has all these clients, so we can see the mobile version, the web version, the desktop version, and so on. And all of them interact with the same backend. So the most popular one, I guess, and the one I found the most in the engagements was the web extension with this autofill feature that we can see on the right. And at least what I saw the most. So this is what we're going to study. And as well of the login methods, we have a lot of ones, including some that are really useful for corporate environments, as we have single sign-on and so on. And we also have this additional factor that we can append to it. So for example, a time-based one-time password. So for this case study, we're going to be using the latest Bitwarden version. Same for Chrome. Chrome because it's the most popular browser. Same. An up-to-date Windows 11 for the same reason, most popular one and the one we saw the most in corporate environment. And we are going to be looking at targeting a user which uses password and a time-based one-time password authentication. And so with all these elements in mind, we can create our case study scenario. And it's really important to understand that we are in a post-compromission situation where attackers have already a command execution capability on the target. So it could be through phishing, for example, or through lateral movement. We often do that to target admin workstations. We already are on the network. We elevated our privileges and so on. And we're targeting the administrators who are basically using a password manager to get every secret of the network. So in this talk, we'll be using Cobalt Strike as an interface between the attack and the machine, but it could basically be anything else. Just understand that we already have a foothold on the machine before the study. So now that we know a bit more about the scenario, let's dive really into Bitwarden. So a great piece of documentation when you are interested in Bitwarden is the white paper, which basically explains anything you need to know about the software. So I highly recommend it if you want to dig the subject. And to sum up the authentication process in a few words, we have this Bitwarden server, which is common to any client. And what happens is that you will log in using your favorite client, here the web extension. And it takes your email and a password, and it puts it in a cryptographic function. We won't go into details here, but you end up with two elements, the stretched master key and the master password hash. And this master password hash, in combination with the multi-factor authentication, will be used to connect to the Bitwarden server, and the communication will be made authenticated through bearer tokens, quite generic way to interact with a web server. And then it will output, once you're logged in, the encrypted database, which is a JSON file with encrypted strings inside. And it will be decrypted using the stretch master key. And then, voila, you got your password. So this is how it works under the hood. And what happens is that what we detail here, there are sometimes some data which goes a bit through the authentication process. And these interesting data are the bearer token, which is used to authenticate to the database. There is also the encrypted database, which could be an interesting piece of information. There is also the encryption key, which in this situation, it's symmetric encryption, so it's the same as the decryption key. But if you use Bitwarden in an organization and to share passwords and share accounts, sometimes it's asymmetric encryption, but in our case, it will be the same. And you have the decrypted database too, which are all of these elements are interesting for an attacker because access to these elements could mean having access to your passwords. And so each of these elements, they are stored somewhere. We have basically, because it's a web extension, it's stored for the most part in the browser. So you have in the local storage, in the browser session storage, and some of them, including the decrypted database, are only available at runtime in JavaScript variables. So it's not per se stored in the browser. It's just it's a temporary held in variables. And each of these storage locations, they also have a location on the computer per se. And it could be here either on disk or in memory. And the most interesting one, obviously, are the decryption key and the decrypted database. And these ones are accessible in memory, of course, but only once the database is unlocked. It's not all the time. When you open your computer, you won't have your decryption key of Bitwarden in your browser, but in runtime, when you unlock your database, it will be found in memory. And so, as an attacker, what I want to access is the decrypted database. So let's start by looking for it in memory. And so accessing memory of a process, here the web browser, can be done through various means, but here we'll be talking about memory dump utilities. There are lots of them. We won't go into details here, but there are some which are official. For example, the task manager, Windows Task Manager by default, lets you extract make a memory dump of a process. You have the famous proc dump utility. You even have a Windows API for that. And you also have the official but not so expected ones, also known as the lol beans in the penetration testing and security community. We have, for example, Steam, the game launcher, which lets you do process dumps. So why not? What you have to understand here is that it's actually not that easy to prevent process dump, and attackers will often find a way to do so because there are lots of ways to do. And so once you have this process dump, as an attacker, you can search for clear text in memory. So this was already researched. I don't want to mispronounce the name, sorry, but he's in the room and he was on stage right before me. But this was quite well studied last year, and it ended up developing in the development of Pandora, which is a tool to analyze these process dumps and find clear text passwords from memory. And so this is applied to my sample database, and you can see that we have the password, the username for various accounts. So it works well, right? But it does not immediately get the whole database, which is in fact made of multiple pieces, which may or may not be found in this pattern that the tool uses to find in memory the passwords. But when we look at this slide again, we can see that another interesting piece of data is found in memory. It's the encryption key. And if we are able to find this encryption key in memory, and as well as the encrypted database, which is easily recoverable from disk, we can get the same result, but get the whole database and not just pieces that we're able to get clear text passwords in memory, for example. So let's do that. Let's try to find the encryption key in memory. So here it's just a proc dump, and I just run a quick search on it with a known encryption key that I had, so I saw that there were occurrences. And let's try to discover a pattern for it. So to make my quick and dirty pattern discovery, what I did is that I started by dumping process memory in various situations. So for example, different versions of Windows, different Bitwarden databases, different Chrome versions, and so on. Then I went for my known encryption keys and start to identify bytes before and after my encryption keys to see if I could get a pattern that emerges from this search, and we'll do statistics, we'll try to get rid of outliers and so on, and eventually try to get a regex that, taken any process dump, is able to get the encryption key from the dump. And what's interesting to notice is that if you are able with the regex to match, let's say not 1 million, but a few hundreds of potential encryption key, you can still brute force the encrypted database with it. It will be done offline, so it's not the regex does not have to match exactly the encryption key. You can get a few outliers, and eventually it should work. So I made a quick program to identify, to semi-automate the pattern identification. So I'm just going to loop through my dumps. So here you have a Windows 10 dump, another one, but after a restart and so on. And we'll see that we are able to match the encryption keys and get the bytes, the few bytes before, the few bytes after. And from these bytes, we are going to try to combine them. So for each match, we'll try to get a pattern to extract outliers, a few statistics, and so on. It's a bit dirty, but eventually, in the end, I was able to get a pattern with XX symbolizing that it could be any byte, but this in front of 32 bytes should find you the encryption key. And so the attack plan here is first to get the encrypted database from disk. Should be done easily because it's in the local storage, it's stored on an accessible file. Then wait for the user to unlock the vault, dump at this moment, or a bit after, it does not have to be at the exact moment, the process, parse with our regex that we just built for encryption key candidates. We are okay with having not a single one, but a few candidates, so we are going to test them against the encrypted database, and eventually profit having our decrypted database and being able to hack the client. So, small demo. To get the encrypted database from disk from Cobalt Strike here, it's already included in the software, so we just use the built-in software capabilities. This file, it's where it's located. It's accessible from a non-administrator account, and you can just get it, and then you parse it with a specific tool. I won't go into the details, but just understand that it's easy to get the encrypted database. Then we wait for the user to unlock the vault. And we'll be dumping the process memory. So first, there are multiple Chrome processes, so you have to select the appropriate one. It has an argument. It's launched with the extension process arg. So you can just target this one. And then I'll be using one or the other. It doesn't really matter. A way to get proc dump. So here it's from Cobalt Strike. But in the end, what we have is a process dump. And we'll be using our regex. So I wrote, once again, a small program you get its inputs are the Chrome dump that we just did, and then the encrypted database. It will parse the memory dump. It will find, with the regex 9 here, encryption key candidates. We'll try to brute force the database, the encrypted database, and eventually find the appropriate decryption key. And it will write the decrypted database on disk. So here we have a way to get the whole database and not just a few passwords. So I think it works pretty well. And eventually, with this decrypted JSON file, if we look at the login entry, yeah, we have our passwords. And it's in a well formatted because it's the official database format. So now that we talk about this memory parsing, if we go back to our to this slide, we can also notice something interesting. It's that all of the storage location actually in the browser are accessible by JavaScript. So it makes JavaScript a prime target, JavaScript execution a prime target to extract passwords, because it basically can access any piece of interesting data here. So the attack path here would be to either to execute JavaScript in the context of the extension on the fly and try to get our decryption key or our decrypted database, or maybe just backdoor the existing JavaScript pages of Bitwarden, and from then we can just wait for the user to open, and we won't have to to be there at all time, to be at the right time, like for the proc dump, we just backdoor, and then next time he opens, we'll be able to extract the passwords. So here is a sample payload. We won't go into each line here, but what you can see is the Chrome storage access in order to get the local storage, the session storage, which holds the ciphers, the encrypted ciphers, as well as the decryption key. So it's enough, this simple snippet, to get access to the whole database if we are able to run it. And as well as backdooring targets, we have two interesting files here, which are the main.js and background.js, which are basically the front end and the back end of the extension, we could say that. And each of these files, it has there are functions which are related to decrypting the database and getting access to the entries. So if we are able to backdoor one of these functions, we are basically able to get access to the decrypted database. So we can build simple payloads. So this line, it's a line which already exists in main.js and which holds the decrypted database in the I variable. So now we can just extract these variables through, for example, in the local storage, we add a new entry, and the attacker, because it's easy to access local storage, he can just get it from there, or just extract it in the web, on a webhook, for example, and just post the decrypted database right from there. And so now we're going to see how can we execute in the context of the browser our JavaScript code. And the first one that comes in mind is the Chrome remote debugging failure. It's well-known one, and it was abused extensively in the past by attackers. So it's a WebSocket API, basically, to the Chrome DevTools. And once you have access to the Chrome DevTools, you have basically access to the whole browser where you have compromised it. And it can be set up through command line arguments, but we won't go into details once again. But it was patched. In the latest version of Chrome, they patched, but still they can be used if you add an additional parameter. Basically what it means is that it should point not to the default user directory, which holds his variables in his extensions, but to a non-default one, which basically does not exist in this. So attackers, in theory, they cannot do that. But you just have to duplicate an existing profile, and then you point to that profile, the duplicated one, and you can use the remote debugger. So the attack plan here would be to first duplicate the existing user directory, then backdoor any Chrome shortcut we encounter so that when the user double-clicks on it, it will be launched with the arguments. Then wait once again for the user to unlock the vault. We can then access the debugging console, the API, which is made available, and then run the JavaScript payload that we detailed in a few slides ago, and hopefully profit. So demo time now. First step will be to duplicate the user directory. So I created a small code snippet for CobbleStrike. Won't go into details, but it will be made available. It's not yet public, but I see no reason not to make it. And so we launched the program, and it tells us, yeah, I did copy the user directory, and then I found a shortcut that I backdoored, and we can see it's a bit small maybe, but we can see that it added the interesting parameters which let us set up the remote debugging. And it tells us on the next browser restart, remote debugger will be made available on a local host port. But to access this local host port, we have to proxify the request, because as an attacker, obviously, we do not have direct access to it from our attacker machine. So we just set up a SOX proxy here using CobbleStrike built-in capabilities, and we should be able to get access to the remote debugging API on next browser restart. So yeah, we wait for the user to unlock its vault, as usual. And then we'll try to access the debugging console remotely from our attacker machine. So it will have to go through the proxies. We use proxy chains here. And we just do a simple web request on an endpoint exposed by the Chrome debugging API. And it will output a list of URLs, of debugging URLs that can be then accessed with WebSockets. So you have this one, for example, which is the one associated with the background.js of our Bitwarden extension. And then we can connect to this WebSocket and through the debugging capabilities run JavaScript payload in the context of Bitwarden. So we'll start by building the payload. This is a JSON that it's the format accepted by the WebSocket API, but what you need to see here is just that we just want to print the Chrome storage, the Chrome session storage to get the decryption key. So we'll be connecting using proxy chains again, a WebSocket client, anyone would do, the URL that we saw earlier, and we're connected to it. Now we just have to paste our payload, our JSON payload, with the Chrome storage access, and hopefully we get the session storage back, and we can see the decryption key here. So we can profit now. I wrote a small tool. Once again, as an input, he gets the encryption key and the database, and now it just writes the decrypted database. So this works well too by using these Chrome debugging features. And as I said, another way to run our JavaScript payloads would be to backdoor the existing extension pages, namely background.js and main.js. And we have this extension. It's actually on disk, the extension files. We can find it, and it's accessible from a standard user, no need for admin rights. And so we can just browse to it and edit the background.js, and hopefully we are able to backdoor the extension and include our JavaScript. But when we do so, actually, it won't work because the extension will be flagged as corrupted because there is an integrity check on the files, and you can just edit the files, add your backdoor, and hope that it will work like so. So we'll be asking ourselves the question, how are Chrome extension installed? And the usual way would be through the Chrome Web Store. And just add to Chrome and so on. But there is also this developer mode which lets you load extensions from disk. And it's called Unpack extension because there will be just the extension files, not the CRX for those who are installing extensions in the web store. Sometimes you see CRX, which is being downloaded, but this time it's unpacked. And when you do that, it's written in the secure preferences file, which is a file which holds basically any configuration of your browser, such as the themes and the extensions and so on. And there are two entries in this preferences file, which are the developer mode, which you can set to true here, and also the path to an extension. So here it's the path to Bitwarden, and we can replace it by a local path on disk to load the extension from disk in an unpacked format because developer mode would be enabled. And so it's a way basically to reproduce the installation technique from the developer mode, but manually from a malware, for example. And this secure preferences file, there are once again here some verification, some integrity checks, but it's based on information which are available to the attacker. So we can reproduce the integrity check and make sure that we are able to edit this secure preferences file, but still pass the integrity check. So this was described extensively in a research article a few years back. And so let's try to backdoor our extension again with that knowledge by not just modifying the background.js, but go through the secure preferences file and so on. So the attack plan now would be to drop the unpacked extension to disk, the backdoored one, then update this secure preferences file to load the extension by recomputing the integrity checks and so on, and then wait for the user to unlock its vault as usual. But this time we will not have to monitor it because the extension will be backdoored already, so we just wait for him to open, and then we'll get, if everything works well, the decrypted database straight away. So demo time, we start by dropping the unpacked extension to disk. And so Cobalt Strike does not offer capability to drop folders. So we'll be doing that file by file, or we could also automate with a script. But last time I did it, it was like so. And eventually, we'll have to download the secure preferences file to then update it and then put it back. So we'll just make a download. It's not locked. The file is not locked, so we can override it. It's no problem. We download it, then small tool to update it, to do the crypto stuff, the integrity checks. We need the user SID for that, but it's an information that an attacker can get quite easily. And eventually, we are able to upload it back, and it now points to our unpacked extension. So next time the user unlocks his vault, now we receive a callback. This time it's on a webhook, and the base64 data that we can see on the bottom, it's the database. So we just have to decode it, and we get the decrypted database once again by backdooring the extension. There are also ways to do cross-extension data extraction. For example, you install a malicious extension from the web store to a user computer, and you can still extract data from another extension. It's a bit complex, so there are these articles and this talk at DEF CON, the last one, but I won't go into details here. I will let you just visit these resources if you're interested in this subject. And so one last technique here is process injection, which is an old classic that still holds an important place here, because let's remind first what process injection is. It's just running, basically it's just running code in the context of a targeted process. So this time the process will be Chrome. So here is just a short summary. We just inject a DLL, and we see that it's running from the target process. Won't go into details here, but you get the idea. And so what can we do once we are executing code in the process, running code in the process Chrome? Well, we can start by parsing memory to find the encryption key like we did before, because we're in the process. We can just read our own process memory. But what we can do too is function hooking. So function hooking, basically it's intercepting the calls to various Windows functions, and on the fly either access the data or modifying it. An interesting function in this case to hook would be the one related to files. So the one we are able to read the file's content or the file's attributes. And the idea is to hook these functions and trick the browser into loading a fake JavaScript, a backdoor. We are going to do the same. We are going to include a backdoor in the loaded files, but this time not from disk, directly from memory, from a process injection. So the attack plan here is to first inject in the Chrome process. Then we are going to hook these function calls, replace on the fly the JavaScript by a backdoor version, and then hopefully profit and get our database once again. But it's not that easy, because injecting in Chrome process, there are quite a few mitigation policies that you can see on the left, but we can still manage through various means. And in this example, I'll be using com hijack, but won't go into details once again. But what we have to understand here is that I'm able to run code in the context of Chrome browser. So now we are hooking function calls to any function, basically, which is involved in reading the extension files. So we are setting up our hooks, and then we just identified that the Chrome here was trying to get access to this main.js file. So now that we identified that, we are going to be modifying any further call related to this file to load our backdoor inside. So we are going to update, for example, the file size, because there is an additional line, and also the file content. And now we can use any of our JavaScript payload that we detailed already, and so on and so on. You know the drill now. And so basically, we described a few techniques here that could work to extract passwords from Bitwarden, but how about other password managers? That's the question that I asked myself, because I developed this technique good, but now what if my client is using LastPass, for example, or Keeper? So let's see for each technique: parsing memory dumps, Chrome remote debugging, extension backdoor, browser process injection. would they apply to any other password manager? And the answer, in theory, at least, is yes, because, for example, for the encryption key, Chrome needs to have it somewhere, because otherwise you won't be able to access your database. So basically, it's just a matter of modifying your memory patterns in order to get access to it. As well as for the others, it's just a matter of your JavaScript payload. You just have to adapt it, but because there is always a front end, a back end for your extensions, it does not really matter which password manager you're using. It should, in theory, always be possible to get access to the passwords. And we also talked mostly about Chromium-based with the secure preferences file, with the Chrome remote debugging. But in fact, it should also work with Firefox, for example, because, once again, just adjusting the memory patterns, but it's somewhere in memory, so we just have to find where. And as well as the debugging failures, it seems to exist with this parameter, but I have not been testing it yet, but that's what I read online. Same for the extension. It should be possible to do XPY sideloading. It's the extension format for Firefox. I haven't tested it yet, so maybe for next year, or I don't know, but here are just clues and some ideas where to look for. And same browser process injection. The browser needs to read files, or needs it has functions that it uses, so we can always hook them and alter how it works at runtime. And basically, anything else could work. When you take a step back, you could have a keylogger, you could replace chrome.exe. Maybe you have another ID, but anything could work to extract this password. So is it because Bitwarden and all of them are not safe? Not really. It comes down to these immutable laws of security. I don't know if you already heard of them, but in theory, nothing can prevent an attacker which has code execution on your machine. This is the root cause. From accessing passwords in memory or through various other means, once an attacker has access to your system, it's not your system anymore. It's basically what these laws say, these so-called immutable laws made by Microsoft. I think it was like 20 years ago, so it still holds on its title of immutable laws. So quite an alarming statement for a lot of people who hear this for the first time, but what can we do, in fact, about it? Well, some password managers, like Keeper, tried a kernel module protection, which makes the Chrome process highly protected against, for example, process dumps and so on. So, in fact, it works. It does work. It prevents an attacker from making a process dump and parsing the key in memory. However, it's quite an assumption, but it just needs an administrator access, for example, through a lateral movement. We often get that during engagements, to be able to access kernel, because according to Microsoft, administrator to kernel is not a security boundary. So it's expected for an administrator to be able to run in kernel. Why not? OK, Microsoft. And also, these kernel modules, well, we saw with CrowdStrike, for example, that they sometimes can be worse than attackers and crash your system. So I'm not personally a huge fan of this kernel module. Why not? Maybe we'll see in the future how it goes, but I'm not sure it's a silver bullet. And sometimes it's a bit overstated its capabilities. So the real protection, I would say, is to protect your admin workstation. The standard users, you can't really do anything to protect them, but your administrators, which holds really the most important secrets of your networks, you have to protect them through network segmentation, through the principles of least privilege. Once again, these principles were there before I was born, I guess. And so you can just go to your get a guide from your. This was from France's recommendation from the agency in charge of protecting computer security. There are plenty of them, but it always gets down to the principle of least privilege, network segmentation, hardening, and basically, if an attacker can't access your admin network, he would, in theory, and most importantly, never get a code execution to it. You should be okay. And there are always these hardening measures like EDR, app locker, and so on, the classic ones, I guess. If anyone has another idea to share, I'd be welcome to have them, but it's the classics. A few ideas still for Chrome developers, even if I'm way, way, way less competent than they are, because it's their software, basically they know better than me how it works, but still a few suggestions or maybe talking points, and I'm sure they already considered all of them, and it's not that they do not want to secure their product, it's more that maybe it's useless, maybe it's hard to implement, but a few ideas would be, for example, to get a separate build for developers, because these features like remote debugging, like extension, developer mode, could be reserved to developers, and the standard user won't have these features in the browser. We could also add an encryption layer to the secure preferences file, but we'll have the same problem. Where is the encryption key and so on? We could also verify the signature of COM-loaded DLLs. This was for the process injection stuff. And also avoid hard-coded extension rights. This one we did not talk about, but it's about cross-extension. So here are a few talking points maybe for them, but I'm sure they already considered most of it. So here it is. Across this talk, we kind of saw how it was possible through various means to extract passwords from basically, I guess, in theory, any web-based password managers. And it all comes down to the immutable laws of cybersecurity. And maybe you won't never be able to prevent an attacker from doing so. So you will have to apply these decades-old measures of principle of least privileges and so on. And so, yeah, basically, that was it. I'm just adding a few acknowledgements for my company Orange Cyber Defense, because it's thanks to them that I have time to do that on my work time to do this research, and especially Claire and Jean-Pascal, which are responsible for the research team in the company, and which let us come with this research. And a huge thanks to BruCON for the whole organization, for the talks, for the workshops, and for having me, for inviting me. So a huge thanks to them.
So I think my mother-in-law has the perfect solution, because she writes her passwords in a physical notebook. So that may be a solution as well. Wouldn't it just be simpler to not use browser extensions for passwords? Because then you would circumvent the whole JavaScript issue, which is apparently at the root cause of all of this, and just use, like the application. We have Keeper, we just use the application. You can probably still dump the key from memory because it needs to be somewhere, but it makes it a lot harder, I guess, than using browser extensions.
It's an interesting take, and eventually it always comes down to the at what cost for the user ease of use you are ready to, how much you are able to sacrifice on the user friendliness of your app, because users, it comes from the user they want to have this browser extension, but in fact, yeah, you could get rid of it, maybe gain a bit more security, but basically what I did with KeePass was the same. I did a lot of research on KeePass, and you could end up with tens of methods to extract the database. So I don't really think it would be enough. It may be a good idea, but KeePass was the same. You could do DLL sideloading, you could poison its configuration to just spill the password and so on. So I think it always comes down to the immutable laws of cybersecurity. But in fact, you could cut like a few of these attacks by not using the extension.
Yeah, but dumping process memory would be one of the things for Keeper that you would do, and that would make a lot more noise than modifying JavaScript. And stuff.
Also noise is an interesting data to take into account, because having the capability to extract, it's a thing, but having the capability to do that and not be detected is also quite important for attackers. So yeah, the less ways you have to extract, the more you can focus our detection on these few ways, and I do agree on this point.
Right. Thank you.
Yes, I was just wondering, as more of a side thought, how would this, or your opinion on privileged access solutions like CyberArk, Delinea, that also have a web-based interface. It's not using browser extensions mostly, but are they also vulnerable to these kind of attacks, or do you have any experience with that?
If I remember well, it's still in the browser, right?
Sorry?
It's still running in the browser, right? It's
yeah,
through a URL that you access.
The interface through a browser. It's a central vault that you access.
Well,
like
if we come back to the techniques, we can see that basically the remote debugging will still work. The memory parsing will still work too. The extension backdoor per se won't work, but we can still install a malicious extension which has access to the page. So we could have a way through installing an extension to make it work. And browser process injection should work too. So once again, it comes down to the immutable law. I guess no solution is safe, but I'd be glad to see a password manager which would claim to protect against these techniques and see how it holds. But I do believe in theory, it all comes down to detection and to be able to see when it happens, rather than trying to prevent it.
Okay, thank you.
Have you experienced like meeting honeypots or anything else that really slows you down or says, okay, now I should stop and think more before I continue? Are there any stuff like that you would highly recommend people to do on the blue side so that your work gets more difficult?
Yeah, in fact, well, the first one was when I encountered for the first time a Bitwarden. I was like, oh, I only do KeePass, sorry, won't be able to do so. But it's more of a technical and development point, so it's not really something that the blue team can set up. Detection and deception are really good ways to do so, like having honeypots, making me think that there is something to extract here and there. And personally, if I just see if I sometimes encounter stuff like that, well, sometimes you know that there is a really capable security operations center in front of you that really will see anything that you do, and we don't even try. But it's more something that we feel from what we encounter on the internal network. But I don't have a particular stuff in mind, but maybe this one, when you can't even reach the administrator workstation, then basically you will be stuck, and it happens sometimes. There are, like, I would say 5 to 10% of the time, when it's well done, we are not even able to reach the workstation where the password manager is executed, so we won't even be able to get access to the password then. But I'm not sure it answers really well your question. But
Wonderful presentation, also very scary. Thank you for that. We're here considering the option of TPMs. There are these hardware modules that are specifically made for cryptographic operations, like encryption, decryption, such that there is an environment where the encryption key can be securely stored, cannot be fetched by normal processes and such. Do you have insight in these kinds of hardware modules, and could they offer a solution?
Well, I do not personally have insight, but I do think it's a great idea, and I think maybe Apple started to do stuff like that for their encryption key, right? And it could be a good way to proceed. However, we should always be aware that on runtime, if a standard user is able to encrypt his database, well, he is in possession of the encryption key. So I would be really interested to see what's the flow that what path takes the encryption key from the TPM to runtime memory to decrypt that. I think it's maybe a good research subject for me. Thank you very much.
After having done all this research, do you still use password managers yourself?
Well, I'd say pen and paper is always a great password manager. But I do personally use Bitwarden, the irony. And I have confidence that it worth what it's worth, but that no attacker has execution capability at the moment on my computer. But if he does, well, I know that my passwords may get stolen. But it all comes down to the trust I put in the fact that my computer is not compromised.
So one of the immutable laws.
Thank you for presentation. Is the point of all this presentation is to think about the fact that we doesn't have to rely on password anymore for connection?
Well, once you're connected, an attacker can still get your cookies after. So it's not really comes down to the password itself. The idea was more to make people aware that it was not a silver bullet having a password manager, and that these ones are really important to get in your network. Passwordless, I don't think it would prevent session to stall session, to get impersonation at runtime. So yeah, I'm not per se a passwordless advocate, but it's not really my expertise neither. So I don't really have an opinion on that. But intuitively, I would say that it won't change a lot for attackers.
Thank you.
Thank you.